Today we're going to do a little review for exam what? 6, 7, 6, 6. Close it too far. Cut off all our circulation. Okay. We're going to do this review. I'm not sure how long it'll take, but then I want to get into a discussion of the lab we're going to do today. Introductory there. And then the lab, and it shouldn't be, actually, it's really simple. Really simple. Simple's good. Okay. So we're talking about bonding general concepts. And I'm going to use version 1 of our review documents. I've got several marked off here. In fact, nearly every one for the first couple of pages, which is okay. Get the ball rolling. Okay, so let's look at number 1. Here we go. This is basic stuff. I mean, this is more physics than it is chemistry. Right, the force between two bodies having identical electric charges. You have the same charge. You can't push them close to each other without feeling a repulsive force. So you feel this repulsive force, and all the rest are just stupid answers. That's the only one that makes any sense at all. They repel one another. All right, atoms having equal or nearly equal electronegativities are expected to form. Looks like we're looking for what type of bond they form. If they have equal electronegativities, they're going to, first of all, they're going to form covalent bonds. They have to share electrons. There's no transfer of electrons completely in order to make an ionic compound. And then on top of that, it's not only nonpolar, it's not only covalent, but it's nonpolar. In other words, nobody wins. They either share or there's no bond. For the elements cesium, fluorine, and chlorine, the order of increasing electronegativity. Okay, got this one right. Left to right is increasing. So what I would do to answer this one is look at the choices and say, all right, which one has the greatest electronegativity? Fluorine's easy. I mean, it's the biggest one on the table at Pauling's 4.0. So this one has to go last on the right-hand side of the greater than mark. So it's either this one or that one. Then you have to say, all right, what order are these two guys in? That one and that one. Cesium's the lower left, right? It's got to be the smallest one. That means chlorine's in the middle. So B is the only logical answer to this one. Okay, the electron pair in a carbon-fluorine bond could be considered the electron pair in a carbon-fluorine bond. Looks like it's looking for where they're located. Closer to carbon, because carbon has a larger radius? I don't think so. We're talking electronegativities again. It's going to be closer to fluorine. But apparently they're looking for a reason why too. Closer to fluorine, this is the only one that's closer to fluorine because fluorine has higher electronegativity. That's it. It's the only one that makes sense. All right, 5. Yep, 5. Which of the following molecules has no dipole moment? All right, we have to look at what two things determine dipole for the entire molecule. Right. 1, bond polarity. Does the molecule have polar bonds? If you want the whole molecule to be polar, the bonds have to be polar. If the bonds are nonpolar, you can stop there. You don't need the second one, which is geometry. Okay, so let's look. Carbon-oxygen bonds, yeah, they're going to be polar. Nitrogen, hydrogen bonds will be polar. Hydrogen-oxygen bonds will be very polar. So we have to look at geometry. So what's the geometry? Well, if you don't remember, then you're going to have to draw the Lewis dot structure and use VSEPR to tell you what the geometry is. But if you remember, having done it before, carbon dioxide is like this. Ammonia is like this. Actually, that's in the back. Okay. There. So we got a trigonal pyramid shape with polar bonds that add up to a polar molecule. They're going to be this way for each of them. And it adds up to a total like that. Now we just look at this one. If the bonds are polar this way and this way, they're equal and opposite, so they cancel out. This one is nonpolar. No dipole moment for that. Right. And of course, we know water is a bent molecule. Right. And that's a dipole moment like that. So carbon dioxide is your ticket. All right, 5. Yep, 6. Which of the following has the smallest radius? Right. This one's kind of tricky because these are all ions. Okay. And the trends that we discussed for atomic radius were neutral atoms. So I think we need to approach this one differently. Let's first use the concept of isoelectric. So can we use that? Let's look at the periodic table. Right, potassium. Okay, potassium 1 plus is going to look like argon, and there's argon. So potassium and argon are isoelectric. How about chlorine? Yep, chlorine 1 minus is like argon. Rubidium, now rubidium's off by itself, so we can't use it for that one. How about sulfur 2 minus? Yep. So these and these all look like argon. They're isoelectronic. So if they have the same number of electrons, then what determines their radius? The number of protons. The strength of attraction for those electrons that remain. So which one has the most number of protons in that group? I think potassium does, doesn't it? Yeah. Go this way and then down to potassium. So potassium has the greatest number of protons. Then we have to look with rubidium's the fly in the ointment here. Where would it go? Well, rubidium is way, way down here, isn't it? No, that's radium. Here's rubidium. Rubidium has an extra. In fact, it's the 5th period, and potassium is the 4th period. So rubidium is not isoelectronic, but it has an extra layer of electrons. It's a period 5. So it's got to be bigger than potassium. We don't care if it's any bigger than the rest of them because no potassium is the smallest of all of these guys. So we compare rubidium to that one. And rubidium, let's see, rubidium plus has to be bigger than potassium. So potassium's our answer. That's the smallest radius out of that bunch. It took some mental gyrations, I admit. 6, 7, 7. Okay, which of the following arrangements is in order of decreasing size? Okay, let's see. Decreasing size. I'm looking to see if it's presented properly. Yeah, we're decreasing to the right, decreasing to the right. Okay, that's good. Order of decreasing size. Okay, let's see. Are we comparing the same ions with each one? It appears we are. So we're looking at gallium, calcium, potassium, chlorine, sulfur. Are those isoelectronic? That's what I'm thinking. Gallium is here. Gallium 3 plus would go 1, 2, 3. That looks more like, no, gallium's the left. Gallium 3 plus would look like argon. And calcium 2 plus, potassium 1 plus, chlorine 1. Okay, so all these are isoelectronic argon. Actually, gallium's not isoelectronic argon. Why is that? Because it has 3D10. These are isoelectronic with argon. All of these right here. Gallium has the extra 3D10s. So that's going to make it for these, of all these. Okay. Then we just have to see what's the order of the rest of them. Right. So we look at the number of protons, and we should go from least number of protons to greatest number. So calcium to potassium, to chlorine to sulfur. Sulfur will be the greatest, would be the, no, sulfur's not the smallest. So this is not right. Sulfur needs to be the biggest. It has the least number of protons. Then chlorine, then potassium, then calcium. And would gallium be the smallest? Gallium has more protons. Gallium has the most number of protons. The problem is those 3D10s. So if we did it like this, well, that's the best answer. We have to assume that gallium is the smallest because it has the most number of protons. I'm just wondering what happened to the 3Ds. Did I talk about it? Did I try to explain that in work problems? Well, the isoelectric argument is there. All right. So I make an argument for the isoelectronic ions, and then I talk about the neutral atoms. Their order would be potassium, calcium. Their order would be potassium is the biggest, then calcium, then gallium, and sulfur. Saying that gallium is the smallest based on the number of protons. All right. This is the one that I'm not convinced about. But the rest of them, don't put these in the right order. So for that reason, I'd go with this one. The rest of them have the wrong order for all of these isoelectrons. That's the best I can do right now. Okay. 8. Go. In the reaction between magnesium and sulfur, the magnesium atoms do what? Become anions, become cations, become polyatomics, share electrons. The difference in electronegativities here, actually, you don't need to know the numbers. You just need to know where are they in the periodic table. Magnesium's way over on the left, sulfur's way over on the right. Those have to be ionic. So magnesium being a metal, it's going to lose electrons, and sulfur is going to gain electrons. So magnesium becomes a cation. Choose a molecule with the strongest bond. Okay, this one, the strongest bonds. Let me see how I post that. I got an idea. Is counterintuitive. The strongest bond is going to be between, all right, first approach is the strength of the bond depends on the degree of overlap of orbitals. And when the orbitals are huge, you get less strength in your bonds. So as you move down, these are the halogens in order. As you move down, you get bigger valence orbitals. So the overlap is not complete. I mean, it's not as good. They're further away from the nucleus. So when we do that, we weaken the bond. So I2 is the weakest, bromine is next, chlorine is next. But then you get to fluorine and say, okay, fluorine should be the strongest bond. But then you get two issues that come into play. The distance between the nuclei here is decreasing. Now that's not a problem as long as you get good overlap of your bonding orbitals. But as you get those nuclei closer together and you get the electrons, all the other electrons packed into a smaller area, the core electrons, then you start getting repulsion from both the protons. So the protons are repelling and the electrons are repelling as you get closer and closer. So what happens is when you get this close together with these smaller atoms, you start to feel those repulsive effects. And they counteract the strength of the bond you would expect to develop from overlapping orbitals. So actually, the strength of the bond looks more like this. In other words, it's really weak here, and then it's increasing, then it goes back down. So this is the strongest one right here, the diatomic chloride. And the only reason, well, the reason we follow that line of reasoning is because the evidence says fluorine is weaker than chlorine. I mean, that's the reality. So we've got to explain it. Okay. Now, you weren't given that data here. So you have to work from the explanation backwards to the reality. Okay, let's see. Oh, let's, wait a minute. 10? Oh, 10 is another way of saying the same thing. Which of the following molecules exhibits the greatest bond energy? It's the same thing. Strong bond energy. Just another way of saying the same thing. Okay. This number 11 is going to be based on these molecules. We need to draw the Lewis dot structures for these, and which of the molecules obeys the octet rule. Okay. I think I did boron trihydride in class, and it's deficient. Like that, like that, like that. It only has 6 electrons. 3 plus 3 is 6. They're all used up. So there's no octet here. How about NO2? So we have, let's see, 5 and 12, 17 electrons. So we have 2, 4, 13. That's 6. That's 12. And we have 1 here. 13. Now you can look at it 2 different ways. You can either make a double bond here, and that will make nitrogen exceed the octet. Let's see if that's possible. Where's nitrogen? Here. Nitrogen is in the second period. It has no access to d orbitals. So it's not going to form a double bond here and exceed it and exceed the octet. So we have to leave it like that. And nitrogen has 7. 2, 4, no. 2. No, we do have a double bond. 2, 4, 5, 6, 7. There we go. Yeah, we do have a double bond. But we can't go any further. It's only got 7. Okay, how about SF6? Okay. Let's see, 1, 2, 3, 4, 5. 6 times 7 is 42. And sulfur is in oxygen group, so it's 48 electrons. So if we make an octet around fluorine, that's 6 times 8 is 48. That's it. We're done. 2, 4, 6, 8, 10. Sulfur's got 10. Okay, how about O3? Ozone. Right. 1, 2, 3 times 6 is 18. 2, 4 from 18 is 14. So put 2, 4, 6, 8, 10, 12. 2 there. Okay, now can we make an octet out of this one? Yeah, in fact, we can make one on this side, or we can make one on the other side. So that sets us up for what? Magic word is resonance. We would have to resonate between the two with this model. That's one of the failings of the localized electron model. You have to induce resonance when you have identical Lewis dot structures. Okay, so that one does obey the octet rule. How about PCl5? We found our answer, of course. So phosphorus is what? 5? Yeah, phosphorus is 5. 5 times 7 is 35, 5, 40. 40 electrons. Okay. So if we put an octet around each chlorine, that's 5 times 6 is 30. No, 5 times 8. Excuse me. 5 times 8 is 40. Okay, so that's it. And it exceeds the octet. So ozone is the only one that obeys the octet rule. Let's see. I better scroll this one. There's a little bit of it picking at the bottom if I need it. I'm not even sure if I'm going to need this one. I should have left those structures up there if I'm going to answer this one. Oh, here's an error. That Roman numeral 6, there's no 6 up there. So this must be a 5. Okay, which have 0 net dipole moment. All right. So this one is BH3 would be what? Does it have polar bonds? Boron and hydrogen? Probably. But it's symmetrical. It's a trigonal planar. So this is nonpolar. How about NO2? Let's see, what did we say about NO2? NO. Right? 1, 2, 3. It's going to be bent. It's going to have like that. Nitrogen and oxygen, they're pretty close together, but we should get a little bit this way and a little bit that way. I don't know about that. It's probably polar, most likely. How about SF6? SF6 was 6 groups, which is octahedral, and they're all equal. So this one's non-polar. We're saying this one is polar. How about O3? Each one of the, let's see, we've got one O center, and then we've got, what was it? Like that. 1, 2, 3, 4. Yeah. So this is a bent molecule. The problem for this one even though here's an interesting problem. Even though this is bent, it has this lone pair down here that's going to give a huge negative balance this direction. So I think ozone is polar. That kind of negates my first premise, doesn't it? We don't have any polar bonds here, but we have a polar molecule. Right? So I've got to modify my statement. You can have polar molecules with non-polar bonds if you have these lone pairs positioned correctly. How about PCl5? That one was non-polar, wasn't it? PCl5. It didn't have any lone pairs in it. So it'd be a trigonal bipyramidal. Non-polar. Okay, so that's 5, 3, and 1. 1, 3, and 5. And again, this is based upon actual measurements. We're trying to reason it out. All right. See, that was 12. We're going to look at 13. Yep, we're going to look at 13. Scroll that one. Stop me if you have questions. Or if you think I'm full of hooey. I can explain myself. How many electrons must be shown as bonding or non-bonding? That is, non-bonding are the lone pairs. Actually, that NO2 didn't have a lone pair. It had one free electron. That's got a special name. It's called a free radical. Free radicals are extremely reactive. you maybe hear it in the popular literature, free radicals. You need to get lots of this nutrient and that nutrient to scavenge free radicals in your body because they damage your cells. They do. So one of the things you can take is lots of unsaturated fatty acids, like the 369 variety are unsaturated, and they will scavenge free radicals. There are certain elements in your body that will scavenge free radicals. But they do damage to your cells. What you don't want them to do is get anywhere near your nucleus of your cell. That does some the big C word. Okay, let's answer the question. In a Lewis structure, how many electrons must be shown? This is really simpler than it looks. All you have to do is count up the number of electrons. Okay. So we've got what? 1, 2, 3, 4, 5, 6 hydrogens. That's 6 from hydrogen. We got 6 from oxygen. We got 4 carbons. 4 times 4 is 16. So 12 and 16 is 28. 28 electrons. You have to position them someplace in there. Let me see. Is there a follow-up to that? It's not marked, but since we've already got the number of electrons, let's go to number 14. I don't know why I didn't pick that one. I should have. Okay, we're going to use that same skeleton. And those numbers in this thing, yeah, that's right. Those numbers are just the number of the carbons. They're not 1 carbon here, 2 there, 3 carbons here, 4. No, in this case, they're just numbering the carbons. So we have 28 electrons that have to be positioned. Move that down where I can reach it. Here we go. So with 28 electrons, like this. 28 electrons. The question is, how many electrons are shared between 2 and 3? Okay. We're sneaking in a little bit of organic chemistry here. Yeah, sure. We're sneaking in a little organic chemistry here. With 28 electrons, you still follow the same pattern, drawing a Lewis dot structure. And we've got them all positioned here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So minus 20 gives you 8 electrons that have to be positioned. So now we start working from the outside in. And 2, 4, 6. Where are you going to put the 8? The last pair. If you put the last pair here, that gives this carbon an octet. That's an octet. These guys are left out in the cold. We try to make an octet for every one. So instead of following the rules strictly and just moving to this one, we can't put it over here because that was full. Let's move it over here to this one. If we put a lone pair here, then we've used them all up. And now we can do something about those less than 8 electrons. If it was over here, we'd be stuck. We couldn't put a double bond over. If we put a double bond over here, that would be still be 8 here. That'd be 1, 2, 4, 6, 8. That would be 8 here. This one would be left out. So if we take this one and make a double bond there, that. And that gives us A here, and now this one has 6. We can fix that one with 2 of these and make a double bond here. Okay? So that satisfies the octet for everybody. Okay. In organic terms, this is called an aldehyde with a single double bonded oxygen on the end of the molecule. Only other thing you have is a carbon and hydrogen. So when you hear about various compounds like formaldehyde or other types of aldehydes, that's what they're talking about. All right, do we need anything else? Oh, between 2 and 3, you have 4 electrons shared between 2 and 3. All right. Let's see. Let's get 15. 16. In the Lewis structure for ICl2 minus, don't lose track of that minus sign. How many lone pair electrons are around the central iodine atom? So we got to draw the Lewis dot structure again. Now, chlorine is more electronegative than iodine, so we have to disobey that rule. Right? It's more of a guideline than it is a rule. Put the more electronegative in the center. We're going to take the cue from how it's written. We're going to say iodine's in the center, and then chlorine is attached like that. Symmetry makes more sense than electronegativity in this case. Rather than have a chlorine with an iodine on one side and a chlorine on the other, the chemistry actually says that's the way it forms. And then we have a minus sign. Okay, so we have, let's see, 1, 2, 3 times 7 is 21 plus 1, 22. Okay, we've already used 4 of them. So now we work from the outside in. That'll give us 12 on the chlorines. 6. Is that right? That's 16. No. Yeah, 16, 12, and 4. Okay. We got 6 left. So if we put 2, 4, 6, that exceeds the octet. We can't make any more double bonds because that would exceed for chlorine. And we don't do that unless we have to. So back to the question. How many lone pairs of electrons are around the central atom? 1, 2, 3. 3 lone pairs. Right? The electronic geometry, 1, 2, 3, 4, 5, is a trigonal bipyramid. Trigonal bipyramid in this case, like that, you know, we're going to put the chlorines here. We're going to put the lone pairs on the triangle. So that molecule is linear. And consequently, it's nonpolar. Because these cancel one another out. And these lone pairs cancel each other out too. But when I write it like that, I've got to have that negative charge. But I'll put that negative on there, then the electrons don't balance. All right. Let's see. Let's get down to 19. Oh, scroll time. Oh, we did this one already. When we were drawing the Lewis dot structure for ozone, how many resonance structures did we have? 2. Just depends if you put the double bond between this pair of oxygens or the double bond between this pair of oxygens. Then they have to resonate between those 2. So we've already answered that one. Yes, two resonance structures. 20. Which of the following types of molecules always have a dipole moment? We've got the choice none. So we got to look at every one of them. A linear molecule with two identical bonds. That's nonpolar. If it's linear and both the bonds are identical, then they cancel each other out. So this one's nonpolar. Tetrahedral with four identical bonds, equally spaced. That's redundant. If they're identical bonds in a tetrahedral molecule, they have to be equally spaced. So that's a nonpolar, like carbon tetrachloride. It's a good example. Trigonal pyramid molecule, three identical bonds. A trigonal pyramid. How do you get a trigonal pyramid? You don't get a trigonal pyramid from electronic structure, right? If you've got a trigonal pyramid, like say you got something here, here, and one in the back, that, and then up here, you've got what would be the central atom, just like that. If you have four, let's see, how many bonds do we have? Three. If we had three bonds, and that was it, you'd have a trigonal planar. The only way you can get a trigonal pyramid is to modify the electronic structure for a tetrahedron. So the tetrahedron would have a lone pair up here. Now you would have that in the back. So this one, trigonal pyramid, these bonds can be identical. All these bonds can be identical. That lone pair gives you polarity. So C is a good answer. Actually, we're done. Trigonal planar with three identical bonds, that's nonpolar. This one right here, trigonal pyramid, that's the ticket. Let's see, 2021, let's see. Okay, 21. Increasing electronegativity. The problem with this presentation is we normally think of increasing either from left to right or right to left, as long as they all agree with their sign, with their directional signs. But these are right, right, these are left, left, left. So increasing normally would be this direction, this direction, this direction. But this one is increasing from right to left. So I think that was a mistake. But we have to take it for what it is. So which of the set has increasing electronegativity? Well, if we've got fluorine in each one, which we do, then the fluorine has to be the greatest. So this one would work, that one would work, and this one would work. So we got to choose, throw out A and E, and these are possibles. Then we say, which one will be the least electronegative out of that group? Phosphorus, nitrogen, oxygen. Okay, they're not matching. So we got, this one's the greatest, that's true, that's true, that's true. How about phosphorus, nitrogen, oxygen? Wait, is it in the right order? Phosphorus less than nitrogen, less than oxygen. Less than nitrogen, less than oxygen. Yeah, that's true. So B would be a good answer. Nitrogen, oxygen, chlorine. Chlorine greater than oxygen. No. They're probably close to equal. And then the nitrogen would be over here the least. The nitrogen's in the right place, but the oxygen and chlorine are questionable. So I wouldn't say that's the best answer. Oxygen, sulfur, silicon. Oxygen needs to be greater than sulfur, and sulfur needs to be greater than silicon. This one would be a good candidate too. So if I let one of these slip through on the test, you could argue that even one of these is a good answer. I might go through just as a robot and use my key and say, if you put D in there, I might mark it wrong. But if I do, on something like that, you can come back and get your point. The only way to break the tie is to actually look at the numbers. Right? Look at the electronegativity and see what you got. Yeah, 22. Which choice has the bonds listed in the order of increasing bond energy? Okay. There's several things operating here. Possibilities. The greatest bond to energy we look at this first one. Hydrogens with each one of them. And the electronegativities are in the wrong order. The strength of the bond could be based on two things. One is how electronegative is the halogen. Bromine is less electronegative than chlorine, which would decrease the strength of the bond. So that right there, we don't even have to look at this one. That rules out A. B, this is pretty straightforward. The problem is increasing bond strength, single bond, double bond, triple bond would be okay. The problem for this is that triple bond with oxygen does not exist, at least not in my universe. So even though, if you just focus on the bond itself, actually we should have put something else in here like carbon. That would have been better. Carbon-carbon bond. Increasing bond energy, single bond, double bond, triple bond. I think that's probably what should have been done. Because you can have triple bonds with two carbons. I mean, just acetylene is a good example. We've already found that this one is the greater bond strength for this group. So that one's out. N2 is less than carbon-carbon bond in C2H4. C2H4 is a double bond carbon. And this one is a single bond. Right? You wouldn't know that unless you draw the structure. This one's going to be C, C, and then hydrogens like that. This one's going to be a C, double bond C, and only that many hydrogens. You get 2, 4, 6, 8, 2, 4, 6, 8. And this one, dinitrogen, is triple bond. So it's in the wrong order. If it was flipped around, D would be the best answer. In fact, that would be the best correction for this, is to flip these around. Leave that one alone, because that doesn't exist. Disqualifies this one. That's what should be done. Okay, so as is, we're going to say that this one is the strongest bond. Next one, next one. Even though that's not the, I mean, I don't know, maybe you can get a triple bond out of oxygen. How do you do it? Maybe it's possible. We don't know the rest of the molecule. These are whole molecules, but these are like, they're parts of other molecules, so there's no way to find out. 23. Let me scroll that one. Put it down here. Let's see, does that do? There. Then I can page the next one if it's one of our candidates. in the gas phase, which of the following diatomic molecules would be the most polar? This is just simply what's the difference in electronegativities. And if you're not actually given the values, you look at their relative positions on the periodic table. The most polar would be the farthest away from each other. And we know that lower left is cesium and upper right is fluoride. That solves it right there. That one's going to be the most polar. In fact, it's going to be ionic. Now, if it had said something like, which would be the most polar without being ionic, then we have to look for something that doesn't exist. There's no choice in there that would satisfy that one. All right, 24, let's see, is that one I picked? Let's get down to 25. Which of the following ionic compounds has the largest lattice energy? The lattice energy most favorable to a stable lattice. All right, we're not given any values, so we can't actually calculate the lattice energy. It can be done, but we have to look at what's the definition of the lattice energy. Let's look at that first. So let's use this first one as an example. Barium oxide. Is that a valid compound? Is barium a 2+? Yeah, barium's a 2+. Beryllium is a 2+. Cesium is 1 and iodine's 1. Okay, I'm just checking the compounds to see if they're right. Okay, these are written correctly. So if we look at barium oxide, and these are all solids, right? They're ionic compounds, so they're all solids. So when we're trying to determine the lattice energy, we're going from, actually you can write it one of both ways. Let's write it this way. Barium 2+ as a gas unites with oxygen 2- as a gas. And that makes barium oxide solid. This is going to be extremely exothermic. They're all extremely exothermic, but which one is more extreme? The largest lattice energy is the one that has the greatest negative value, as written. That's the lattice energy. Okay, so what we need to look at is two things. Lattice energy is determined by the size of the charges, and how close they are. Right? That's based upon energy equals some constant times the, let's see, how do we write this? The Q of the cation and the Q of anion divided by the distance between them. Okay, so as they get closer, this gets bigger. As this gets smaller, this gets bigger. As these get larger, this gets bigger. So we need to look at it in those terms. So how about the relative size of the ions? Well, the first thing I would do is go in and look at the charges. So barium and oxygen are 2-, 2+. Beryllium and oxygen also. There's a 1+, 1-, plus those are big ions. Sodium and bromine. Sodium is not that big, but bromine is pretty big. And barium and sulfur are +1 and -2. I mean, +2 and -2. So that one's pretty big, and sulfur's pretty big. So I would eliminate this one and this one based on charge. It's only a single charge. And then I would look at size. The bariums are huge. They would keep the nuclear centers away from each other. And then these are relatively small. So this one should have the the largest lattice energy based on that reason. And then we'd have to go actually look at the values and see if I'm full of hooey again. 25, that was 26. 26. It's just peeking over the edge, so I'm going to have to scroll it. Yeah, we get 26 and 7. If 27 is, yeah, we're going to look at 27 also. 26. The first electron affinity value for oxygen is unfavorable, favorable, and the second electron affinity value is favorable, unfavorable. So by favorable, we mean it's exothermic. Electron affinity gives up energy. So when you're looking at, let's see, oxygen, right? Oxygen gas plus an electron yields an O- gas. That's the first electron affinity. The second electron affinity would be O- gas plus electron yields O2- gas. Okay? So if we look at oxygen in its 2p orbital as, let's see, 6, 2, 4, 8. That, okay. So it's not a strong affinity, but it is, you're gonna add an electron to a neutral atom and help complete one of its orbitals. So this one's probably favorable. So this would be, electron affinity would be give up energy. So it'd be a negative delta. When you try to add an electron to a negative ion, you're facing some pretty sizable repulsive forces. So I'm thinking this one is going to be positive for the second. Okay. And the trend we talked about before, lower left to upper right, you increase affinity, or the negatives get bigger, is only for neutral atoms in the first electron. See, we're introducing another concept here with the second. Second one is unfavorable. So we should have favorable first and unfavorable second. Now that begs the question, in ionic compounds, oxygen forms a 2- ion, right? So if it's unfavorable, how come? Well, that's a different story. You don't just have a free gas atom or ion trying to add an electron to it. You've got another neighbor that is forcing that electron upon you by a metal, usually. So that combination is favorable, but the individual is unfavorable. So there has to be a balance in there. What's the net delta H for the reaction? That's my best explanation for that conundrum. Using the following reaction data, here we go. So we have a delta H for this hydrogen fluorine 2s, okay, and 432 for this one. This is bond energy for H2. This is bond energy for F2. That's the way I read that. You have to put this much energy in to break that bond, put this much energy in to break that bond. And this one, you get that much energy back when these two combine to make that. So we're asked to calculate the energy of the HF bond. So what I'm looking at here is a Hess's law, where you can combine equations to get your target. We need to know what the target is. if you're talking about the HF bond, the energy of the HF bond is put energy in and end up with a free hydrogen atom and a free fluorine atom. That would break this bond and give you individual atoms. That's the target. Okay. So with that in mind, this one has to be flipped. You got to put this one over here, plus you have to take half of it. So we need to go this direction and take half of it. Okay. So that would put HF gas on this side yields 1/2 H2 plus 1/2 F2, and the enthalpy now would be, let's see, can I do that in my head? 271 plus 271 for that reaction. Okay, change the sign, cut it in half. Okay, now we've got these two terms, H2 and F2 over here, that we need to get rid of. But we want the H and the F on this side. So here's the H, here's the F. But we got two of them. We only need one. So these need to be cut in half also. If we do that, then we get 1/2 H2 gas yields H gas. And half of this value, which would be 266. 216. 216. Thank you. 216. Yeah. And half of this one would be 777. Okay. So if I did that right, let's see, I didn't write this one in yet. F2 yields F gas. So is that right? Half of that, half of that, half of this, half of this, half of these. Okay. So let's see. We got this one, this one. We got this one, this one. That one cancels this one cancels that. So that should work. We just need to add this one together. So that's 13, 14, 1, 8, 9, 16. 1 plus 2 is 5. Plus 564 kilojoules. There it is. Okay. The key to this one is writing the correct target equation. Now, if I were mean, I'd put a plus 564 and a minus 564. So if you got it backwards, you come up with the wrong answer. But think about it this way. Bond energies are all positives because they're calculated by how much energy does it take to break the bond. You got to put the energy in, so they're all positives. Okay, 27, 28 is just peeking over the edge. I think I'm going to have 29 also. Let me see if I can get both of them up here. Nope. Okay. Can I page to the next one? Yeah. Yeah, that's good. All right. As indicated by Lewis structures, which of the following would probably not exist as a stable molecule? Okay, we got to write the Lewis structures for these guys. CH3OH is what? Recognize that one? Methanol. Wood alcohol. That's the one that makes you blind. That's the one that moonshiners, when they first start boiling off their mash, that's the fraction they throw out first. It has a lower boiling point than ethanol. So the first jar that they get out of their mash, they throw it out. Otherwise, their customers will go blind, or some of them kill them. Okay, how about this one? So carbon is 4, plus 3 is 7, plus 6 is 13, 14. 14 electrons. So we have C. Oh, the way you write organic compounds, when carbon is followed by hydrogens or anything else, it's bound to the carbon, not to the next atom. So these hydrogens are like this. And then the oxygen is bound there, like that. Okay. 2, 4, 6, 2, 4, 6, 8, 10. So that's 4 electrons. Okay, we can't put any on hydrogen. Carbon's already full, so the 4 have to go here. That's a valid structure. That's probably stable. Or we could go ahead and do the formal charges. Right? All of these are going to be zeros. That's typical for hydrogen. Carbon comes in with 4 and gets 4. Right? 1, 2, 3, 4. So it's 0. Oxygen comes in with 6 valence. 2, 4, 5, 6. It's 0. Okay. So it's got good formal charges. Okay. Which should probably not exist. This one is stable. How about CH2O? Okay, we got carbon, got these 2 hydrogens, and then we got that oxygen. So we got 2, 4, 6, but we come in with 4, 5, 6, 12. Yeah, 12. 12 electrons. 2, 4, 6. 2, 4, 6, 8, 10, 12. All right, we need to have a double on carbon to give it its. So we take these 2, make a double bond. And that's a good Lewis structure. All right, formal charges 1, 2, 3, 4. Yeah, they're all zeros. So that one's stable. All right, how about CH3O? By the way, what was that? I mentioned the name earlier. And that carbon with a double bond on it, that's formaldehyde. This one right here. The simplest of the aldehydes. The one, you ever done the dissections in the biology lab? Yeah, that's what you smell when you open the bag, formaldehyde. Okay, CH3O. C, H3O. So 6, 10, 11, 12, 13. Okay, 2, 4, 6. 2, 4, 6, 7. Did I do that right? 6, 10, 11, 12, 13. Yeah. 2, 4, 6, 8. 2, 4, 6, 8. So that's 5 electrons. 2, 4, 5. So we can take this one to make a double bond, but that leaves 2, 4, 6, 7. That's probably not stable. And it would be 6 comes in with 6. It's got 1, 2, 3, 4, 5. 6 minus 5 is plus 1. So the formal charge on this one is plus 1. That's not a good situation to have this free radical. So that one's probably not stable. Oh, we got our answer. C2H2. Oops, got too many H's. There we go. Actually, it's like this. That's acetylene. 2468, 2468, 1, 2, 3, 4, 0, 0, 0, 0. That's a good one. That's stable. I'm curious about this last one, even though we found the answer. What about this C3H4? 1, 2, 3, 4. That's probably where the H's go anyway. Let's see. 1, 2, 3, 12. 1, 2, 3, 4. 4 and 12 is 16. Got 2, 4, 6, 8, 10, 12. 4 electrons. So where do the electrons go? And you can put them anywhere. Put them there. But now we got to make a, did I count those right? 1, 2, 3, that's 4, 12, 13, 14, 15, 16. Okay. 2, 4, 6, 8, 10, 12. Yeah, 4 electrons. Oh, I forgot the other 2. 2, 4, 6, 8, 10, 12, 14, 16. Okay. Now it makes sense. I was having trouble there for a second. All right. So in order to make the octet, see, 1, 2, 4, 6, 8, 2, 4, 6, 8. This one's only got 2, 4. So we need to take that one and that one and make two double bonds on that carbon. Trying to think, what's the name of this company? Scratch my head. So this one is stable. Based on our Lewis structure. And our answer is C. That one would not be considered stable. All right. I'm looking at 29. Yep, 29. Using the following electronegativity values for these elements, select from the following group that fits the given statement. The molecules contain a carbon atom with trigonal planar geometry. Well, do we even need these? No, we don't. You don't need the electronegativity. All you have to do is draw the Lewis dot structure and invoke VSEPR. Now, if you've got more than one center, then it may have a different geometry than the other, like for this one. Formaldehyde would be, you'd have a hydrogen here instead of the CH3 group. Formaldehyde, this is acetaldehyde, right? And all you have to do to envision where that name comes from, just put another OH out here. Instead of that H, put an OH. And then you have acetic acid. So this is acetaldehyde. Okay, so it's going to look like this. There are your hydrogens. For this one, bound to that carbon. Then you have another hydrogen, like that. Okay, we've got octet, octet, like that. Okay. So what's this one? That's a tetrahedron. 1, 2, 3, 4. Tetrahedral. This one, 1, 2, 3, is trigonal plane. Right? So which one has a trigonal planar? This one. And since it says none of these down here, I guess we're done. We know that this one is linear, carbon dioxide. We've drawn that one before. Around the carbon atom, it specifies carbon. Right? If you look at just this, the oxygen, it has a trigonal planar electronic geometry, but not a molecular geometry. And that's what they're implying here. The molecule has trigonal planar geometry. So we're going beyond the electronic geometry too. So that was linear. This one is CH3 with a chlorine on it. That's 4 groups, right? Methyl chloride. There's another name for that. Chloroform? I think it's chloroform. Anyway, this carbon is tetrahedral. Has 3 bonds here and 1 there. This one has carbon. 6 hydrogens. Okay. These carbons are identical. They're both tetrahedral. Now, if we had C2H4, both of them would be trigonal planar. But that's not the case. Okay, and redundant, 34. Oops, I gotta scroll that one. See if I do it like that. Yeah, let's do it like that. Of the following, which molecule has the largest bond angle? The largest bond angle. Okay, let's work from the bottom up. Water, we know water is like this. Okay, so it's electronic tetrahedral, 1, 2, 3, 4, which means starts out as 109.5. But these two free lone pairs have a tendency to compress the bond angle. So it's probably closer to 107. Something like that. Let's move up. HCN. We've drawn this one before. That's octet. Okay. This one is 180 degrees. That's probably the answer. You can't get any bigger than 180. OF2. That's probably tetrahedral also. And O3. That one is like this, like that. So it's bent. And it's probably trigonal planar. So this is 120. All right. So C is the answer. 180 degrees. That's the biggest angle of the bunch. 34, 35, and 6. I think we've got a few more. How are we doing on time? 10, 20. Another hour. Okay. 35. Which of the following molecules is non-polar overall? All right. So the ones that we've already done and know. We know carbon tetrachloride is a tetrahedron with no lone pairs. Right? So it's non-polar. Got that one done. H2S. Well, that answers the question, actually. H2S is bent. It's kind of like sulfur and oxygen are in the same family. So they're going to have similar profiles. H2O or H2S, they're both going to be bent. So this is polar. SF2. Yes. Okay. So sulfur has 6 and 14 is 20. So 2, 4, 16. That's 12. 4. Okay, that one's bent. Why? Because it's tetrahedral with 2 lone pairs. So this one's polar. SF4. SF4 gives 34. 2 more. So that's 8 times 4 is 32. Okay, we've got a lone pair there. That gives us a trigonal bipyramidal. And if you put 1 lone pair out here, which is where it would go, that gives you a seesaw. So that was polar. And OCl2. So that's 14 and 6 is 20, minus 2, 4 is 16. That'd be 12. 4 left over. That's bent. Okay, so that's polar. All right. So, all right. C is the answer. Carbon tetrachloride is non-polar. The only one in that group that's non-polar. How about 36? Which of the following molecules are non-linear? Okay, so we got multiple choices here, which are non-linear. Non-linear. Which ones are the linear ones? We know this one is linear, right? Hydrocyanic acid or hydrogen cyanide. Carbon dioxide is linear. Okay. Let's look at the others. C2H2. Acetylene. That's linear. Okay. H2O2. Hydrogen peroxide. Let's see. 1, 2, and 12 is 14. 2, 4, 6. 8 electrons. 2, 4, 6, 8. This one's bent here and bent there. That's nonlinear. So this is nonlinear. How about N3 minus? Okay. We have N. So nitrogen is 5 each, right? 15 plus 1 is 16. Okay, so it's 2, 4, 12, 2, 4, 6, 8, 10, 12. So that's got an octet, and this has got an octet. No, but this one doesn't have an octet. So we could either take 2 here and make a triple bond there, 2 here and make a triple bond there, but that would unbalance the formal charges. The formal charges would be best balanced if we take a double bond here and a double bond there. The minus. So this is trigonal planar. Actually, this is linear. This is linear. Oh, so the molecule is linear. Yeah. It doesn't matter what it is over here because these lone pairs don't count. So that molecule is linear. Here. NO2 minus. NO2 minus. So N, oxygen, oxygen, with a minus. So we have 6, 12, 17, 18. That one ion, one electron here. Okay, we've got 2, 4, 14. That's 12. We've got 2 more left. Okay, so what do? Well, we got to take that, or we could do the other side. So this now has 1, 2, 3 groups. That molecule is bent. Right. So that's got where I was going with this. Now, this one is linear. This one is non-linear. So NO2 and H2O2 are non-linear. There we go. All right. (36). Skip down to 38. The molecular structure of BRF6 plus. Okay. I'm game. BRF6. 1, 2, 3, 4, 5, 6. All right. 1, 2, 3, 4, 5, 6, 7. 7 times 7 is 49. 49 minus 1, 48 electrons. Right? Because it's a plus ion. Okay. So 2, 4, 6, 8, 10, 12. 36 electrons. 2, 4, 6. 6 times 6 is 36. That's it. So we have 6 groups here around bromine, which means octahedral. Okay. Oh, this one, octahedral. Are we going to do 39 also? Yep, 39. Okay. Xenon oxyfluoride. Xenon would be in the center. And then we've had oxygen and 2 fluorines. So that's 8 and 14. Actually, 14 and 6 is 20 plus 8, 28. Okay, 2, 4, 6, 22. 6. Yeah, we can put 6 around each one of them. 3 times 6 is 18. That's 4 electrons. Those lone pairs go here. Okay. So what's the electronic geometry of this one? 1, 2, 3, 4, 5. That's a trigonal bipyramid. And so where does everybody go? Well, we want to, I think for the interests of symmetry, but usually the lone pairs in a trigonal pyramid go on the triangle. So that means the rest of them have to go someplace else. Like oxygen here, fluorine there, fluorine there. Like that. I think that in the interest of symmetry, that's better. Because with the trigonal bipyramid, it typically puts the lone pairs on the triangle. We only have one lone pair, then we end up with a seesaw. We have 2 lone pairs, we end up with a T. Right there, there, and there. With this xenon in the center. So T-shaped is the best estimate for this one. All right. Skip down to 44, you can see all of it. Okay. Select the correct molecular structure of SiH4. Silicon tetrahydride. Actually, The proper name for this, well, silicon tetrahydride would be correct, except that there's a better name. It's called silane. And that's derived from this one, which is methane. Meth refers to carbon. So we have silane here. That makes any sense. Okay, what's the structure of that one? Okay, silicon is in the carbon group. Yes. So it has 4 plus 4 is 8 electrons. That's it. We've used them all up, 2, 4, 6, 8. So that would be a tetrahedron, right? Tetrahedron. That was easy. Let's see, we're going to skip down to 48. And it would be chopped off at the bottom. In xenon difluoride, how many pairs of electrons around xenon? What's the molecular geometry? Okay. We have to draw this one. Xenon, 2 fluorines. So this is 7, 14, and 8 is 22. Okay, we've used up 4, which means we have 18 electrons left. And used up 12 more, and that leaves us 6 electrons. Okay, so the electronic geometry here is 1, 2, 3, 4, 1, 2, 3, 4, 5. Trigonal bipyramid. So we have, where we're going to put the, well, we're going to put the lone pairs on the triangle. Fluorines will go out here. Xenons in the middle. Okay, so the, let's see, where are we? Down here. 2, 4. That's a mistake, isn't it? Xenon difluoride. No, it's not a mistake. The answer's wrong. We have 2, 4. Wait a minute. How many pairs of electrons? 3 pairs of electrons. 3 pairs of electrons and the molecule is linear. So this one should be 3. That's tricky. I was counting total electrons, which would have made it E. But 3 pairs of electrons and linear. So that's a mistake in the, make a note of that. That should be 3. What is it in your document? This is the key, so it's going to be a little, maybe a little older. It says 5. Yeah, it should be 3. 3 pairs. All right, that was 48. 49. Choose the member of each set that best matches the label. Okay, so we have 3 answers spread out over these 3 possibilities. Which is more metallic? What do we mean by metallic? More metallic, the lower the electronegativity. That is, the easier it is to give up an electron. So barium would be the more metallic. Okay? So it's got to be this one, or that one. B, C, or E. E. The next one, more covalent. This one's easy. Magnesium and oxygen, those are ionic. So N2O. With this comparison, you just need to say, right, which one's non-metal, which one's metal, non-metal. So N2O would be this one, barium and N2O. Right. So those are the only ones left. Now we have to say highest electronegativity, oxygen, sulfur, bromine. So we look at our periodic table. There's bromine, there's oxygen, there's sulfur. Oxygen is the more electronegative of that group. So there you go. The answer is E. Let's see. We're going to look at 50. Yeah, of course we are. You need to scroll it up. So lots of information for this one. Let's see. There we go. Okay. Use the bond energies below to calculate the enthalpy change for the reaction. Remember how to do this? In order to use the bond energy estimate of enthalpy for a reaction, you got to know the structure of the molecule. You got to know where the single bonds are, the double bonds, the triple bonds, and the atoms that are represented. Now, we're not giving you the whole chart. We're just giving you the ones you need. Right? So we have to write a structural representation of this molecule. And we know that hydrogen cyanide is like this. We know that hydrogen, dihydrogen is like that. And there are two of them. And that yields this one. The nitrogen and two hydrogens. Now there are lone pairs in there, but this method doesn't require accessing the lone pairs. So now that we know that, we sum up the values for our bond energies here and subtract the bond energies there. We do it that way because all bond energies are positive values. So the amount of energy goes in to break those bonds, and then negative, you get it back. Okay, so carbon, hydrogen, 413 for this one. And then two dihydrogens, 432. And then minus oops. I did carbon, hydrogen. There it is. 413 is right. I just left one out. Carbon, nitrogen, triple bond, 891. There you go. This bond, and these two bonds. Two of the same bonds. Now we can subtract 3 carbon hydrogens. Here, 413. And then 1 carbon nitrogen, 305. And then 2 nitrogen hydrogens, 391. There we go. So that's the thinking part without making mistakes. Now we have to do is crunch numbers. 413, 891, add to that. 432 times 2, add that in. And we're going to subtract 3 times 413. And subtract 305. And subtract 391 times 2. And I get minus 158. kilojoules. Okay, that should be the enthalpy of the reaction. Here. Ooh, that one does have a positive in there. Because you get them backwards. So this is an endothermic reaction. Hydrogen and hydrogen cyanide together give you, what is that? Methylamine. Okay. Let me get close. Yeah. Two more multiple choice and then some couple of short answers. This one might take some time. How would we do it on time? Half hour or 15 minutes?
No, 45 minutes.
Oh, 45? Okay, we're good. 50 and then 51. Okay, we can see everything. Actually, I'm going to need a little more room. There we go. Given the following information, calculate the change in enthalpy for this one. That equation. Okay. As is Hess's law. Actually, this tells you what each value represents here. So that's easy. I mean, all you have to do is just use your rules and manipulate. Number 52 is the troublemaker. Right? If you see that one, then it only gives you abbreviations or short versions, and you have to expand them into these equations to make it work. So I think this one would be more instructive to use 52. Especially if you're limited on time. Let's see. There we go. Gives me plenty of working room. All right. So calculate the lattice energy for rubidium chloride from the following data. Right. So our target equation is going to be lattice energy for rubidium chloride. The lattice energy is rubidium ion, cation, gas, plus chloride, gas. Is that right? Rubidium is a +1. Yes. Chloride +1 yields rubidium chloride solid. We want to know what's delta H for that reaction. So that's our target reaction. All right, what do each one of these mean? This is simply the heat of sublimation, solid to gas. We don't have to write a special equation for that. These are a little faint. Maybe interpreted as negative signs, some of them. Those are equal. These are the negatives. The rest are positives. Okay? So this one is given, that one's straightforward. This one, ionization energy 1. So you need to know how to write ionization energy for rubidium. Rubidium, gas, yields rubidium plus gas plus an electron. Right? And the energy is 397.5. These are all kilojoules. Okay. This one is bond energy. So the bond energy is the energy you have to put in to break that bond as a gas. that. And that energy is plus 226. Heats of formation. Remember how to write that one? Start on the right-hand side. Rubidium chloride solid. The most stable form. And then what is it made from? Rubidium solid plus dichlorine gas. And you only need a half of one of those. Okay, that's how you write that one. And this one is minus 431 kilojoules. And this one is it's simple. I'm just drawing a blank right now. Electron affinity. I got it. Chlorine gas plus an electron yields chloride ion gas. And that value is minus 332. Okay. That's what those things mean. If you can't figure that out, I mean, it took me a second for this. If you can't figure that out, then you're stuck. Because you can't have the equations together if you don't know what they are. Okay, now to get to this, we need the rubidium plus gas on that side. Okay, so we need to flip the equation, and there's only one of them, so we just need to change the sign. So we've got rubidium plus gas. Right, this is our target. So this one plus an electron yields rubidium gas element. Now this is minus 397.5. Okay, we use this one. And we've taken care of that one. How about chloride ion? Here's a chloride ion, but it needs to be flipped the other way, doesn't it? So we flip this one around and we put chloride ion gas yields chlorine atom plus electron. And that one now is plus 332. Okay, so we got this one. We used this equation. Now we need rubidium chloride solid. Here it is right here. Formation. So if we're going to have that one, we leave it just like it is. Rubidium solid plus 1/2 Cl2 yields rubidium chloride solid minus 431. We've used this one. Okay. This is the only one left. Okay. So, and we've got everything up here. So, but we do have a problem because we got this one belongs there. This one belongs there. This one belongs there. These guys do not belong. That one does. But wait a minute. CO2. Yeah. Here it is. That's a gas. The phase is very important in this type of problem because we're talking about energy that could be phase change, it could be bond energies, it could be anything. So we have to keep the phase in mind also. So we use this one, and this one. Okay. And the electrons cancel. Electrons Electrons cancel. It's easy. The we've only got one. Oh, I left this one out. Rubidium solid. Here. This one needs to be on the other side. So this one is rubidium gas yields rubidium solid with a minus 85.8. Okay. I knew something was missing. So this one cancels that one. This one cancels that one. Now we have chlorine gas, element chlorine, not the ion, element chlorine, and element chlorine here. Okay, so we have this one available. Cl2, there's Cl2, but we only need one chlorine. So we're going to have to take half of this one and flip it because we need this chlorine right here on the other side to cancel that one. So we're going to take this one and reverse it and take 1/2 of it. So 1/2 of this is chlorine. Like atomic chlorine gas yields 1/2 chlorine 2 gas. And this value is going to be negative 1/2 of that, 113. There we go. So that should cancel this one, and this one should cancel that one. So let's see, we don't have any stragglers in here, do we? Nope. Everybody's accounted for. Okay, now we can add this up. Did I lose anybody? It's complicated, I'll admit. Looks like a good candidate for an extra credit. 332, 431 minus 85.8 minus 13 minus. I think I got them all. I got 99.7. Something went wrong. What did I do wrong? Yeah, we flip that. 332. Oh, there it is. Positive. 431. We didn't flip that. Okay. 85.8. Negative. Yes, we did flip that one. And this one, we flipped and took half of it. That should be right. Maybe I calculated it wrong. 397, I think I did. Yeah, minus 694. Oh, rounded off 695. There you go. I knew something was wrong because my answer wasn't up there. And I wasn't sneaky enough to put none of the above. If I get the wrong answer, then none of the above is the answer, and I'm in a hurry, I'm going to pick that one. And it's wrong. Okay. We got there. That was 52. I think we go to short answers next. Yeah, we got a couple of short answers in the back. Yeah, we got the whole thing in here. Okay. In spite of larger electronegativity differences between bonded atoms of beryllium chloride, beryllium chloride has no dipole while sulfur dichloride does. Explain the difference. If you draw the Lewis dot structure for beryllium chloride, you get, okay, and let's see, 3, right? Or is it 2? Beryllium's 2.
Yeah.
2 plus 14 is 16. So that's 8 and 8 and 16. There we go. So beryllium has less than an octet, and the molecule is linear. So even though you've got a difference in the electronegativities, they cancel one another out. So that's what this statement is here. Beryllium chloride has linear electron pair geometry and linear molecular geometry. So the bond dipoles cancel. Whereas sulfur dichloride, okay, so sulfur is oxygen, right? 6 and 14 is 20. So we have 16, 4. I have 4 electrons left over. That's a bent molecule. Even though it has a tetrahedral electronic pair geometry, the molecular geometry is bent, giving it an overall dipole. All right, one more, I think. Yep. Okay, ICl4 minus. What's the Lewis structure? ICl4 minus. So we have 1, 2, 3, 4, 5, 35 plus 1 is 36 electrons. So if we have 4 times 8 is 32, so that leaves us 4 electrons. Okay. 6 groups around the central atom is electronic geometry is octahedral. So iodine in the center, where are we going to put the lone pairs? Well, in this geometry, the lone pairs like to be out here, rather than on the square. Unlike the trigonal bipyramidal, they like to be on the triangle. So now we've got the chlorines here, 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 and if you put in there lone pairs, go. So that's the electronic geometry and the Lewis structure would be this one. Put in your lone pairs and the charge. Well, this is a representation that works, but this also works. And then the the shape of the molecule. So you just cover these up, and it's a square planar. And then, of course, even though there is polarity in these bonds, they all cancel one another out. Plus, these two cancel each other out too. So that's why it's non-polar. Don't forget the negative charge. Something like this shows up. That's it. For our review, any questions, comments, complaints?